We begin our study of Calculus 3 by looking at vectors in the plane. First, recall that we ended Calculus 2 by examining parametric curves, that is, curves that are represented by a parameterization. The parameterization can be represented as an ordered pair of functions c of t equals x of t comma y of t, where x of t and y of t are called the parametric equations and t is the parameter. Now, parametric equations are used to describe the motion of a particle that cannot be described using a function y of x. In physics, we represent such motion with vectors. There are two types of quantities that we shall consider. The first is scalar quantities, or scalars. These are quantities that can be described only by a number. Example of such quantities: mass, temperature, and energy. We also have vector quantities, or just vectors. These are quantities that need both a number, called a magnitude, and a direction. Examples of vectors: velocity, force, and acceleration. So a vector is simply a quantity that has both magnitude and direction. Vectors are typically represented by a bold letter. Now, if we're doing handwriting, it's really difficult to represent a bold-faced letter. So what we'll do is we'll typically represent it with a letter as an arrow, or typically I do the half arrow. So really, a vector is simply a parameterization. Graphically, the vector in a plane is represented by a directed line segment. So a vector in a plane is simply a two-dimensional vector. The endpoints are called the initial point and the terminal point. The direction of the vector is the direction from the initial point to the terminal point. The length of this directed line segment is called the magnitude of the vector, and is denoted like this. So it's essentially a double absolute value. A vector whose initial point and terminal point are the same is called the zero vector, denoted as a bold 0 or handwriting 0 with an arrow. This is the only vector with no direction. Vectors that have the same magnitude and direction are said to be equivalent vectors, and it will be denoted as v equals w. This allows us to place a vector anywhere we desire in a coordinate system, so long as we do not change the magnitude nor the direction. When an initial point P and a terminal point Q are given, we can also represent the vector as PQ with an arrow over it. So this represents the directed line segment from P to Q. So let's go ahead and sketch a vector. We'll sketch the vector that has initial point 1, 1 and terminal point 8, 5. Okay. So let's go ahead and draw our coordinate system. This is the x-axis, this is the y-axis. And of course, this will not be drawn to scale. So I'll draw 10 ticks along the x-axis, and I'll do the same on the y-axis. So the initial point is 1, 1, so that'd be this point right here. Then we go to terminal point 8, 5. So it's going to draw a line like that. There's 5. Intersection is the point, so now I can go ahead and erase. That's Q. So the directed line segment, I'm just going to draw a line segment from P to Q. And remember, the direction is from initial to terminal. So I put an arrowhead at Q. And this is our vector PQ. Now, just so we can do operations on scalar numbers, on scalars, we can also do vector operations. One such operation is called scalar multiplication. So this is the product of a vector v and a scalar k. And this product is a vector that has magnitude of absolute value of k times the magnitude of v, and it has a direction that is the same as v if k is positive, or its opposite of v if k is negative. As mentioned, this is called scalar multiplication. And graphically, here's how it looks. So this is our vector v. Multiplying it by 2, notice that 2 is positive, so it'll have the same direction. The magnitude just doubles. So this is twice the length of v. Now if we multiply v by a half, again, 1/2 is positive, the direction won't change, but the magnitude will be halved. Multiplying v by -1 is not going to change the magnitude, but since -1 is obviously negative, the direction flips. So it has the same magnitude, but now opposite direction. We also can add two vectors. So we're going to look at the triangle method. And to add vectors using the triangle method, first place the initial point of W at the terminal point of V. And then V plus W is just the vector with initial point that coincides with the initial point of V and terminal point that coincides with the terminal point of W. So graphically, here's V. Notice we put the initial point of W at the terminal point of V. Draw it out. So V plus W will have initial point of V and terminal point of W. And this is why it's called the triangle method, because what you get is a triangle. So if you notice, right, this forms a right triangle. So the sides are V and W, then V plus W would be the hypotenuse. There is another method called the parallelogram method. So in this method, we first place the initial point of W at the initial point of V. We then draw a line from the terminal point of V that is parallel to W. Draw another line from the terminal point of W that is parallel to V. Then the initial point of V plus W is the initial point of V, and the terminal point is the point where the two lines intersect. So graphically, here we have V. We place the initial point of W at the initial point of V. We now draw a line from the terminal point of V that is parallel to 2. Draw a line from the terminal point of W parallel to V. Notice we have then formed a parallelogram. Then our vector sum is the vector that goes from the initial point of V, so the point where V and W meet, up to where the two line segments intersect. We can now define the vector difference. So V minus W as V plus negative W. And then we could use either the triangle method or the parallelogram method. Now, working with vectors this way is rather tedious. It becomes much easier if we consider the vector's component form. So to place a vector in component form, we first need to move the vector so that its initial point is the origin of the Cartesian plane. A vector with the initial point, rho 0, is said to be in standard form. So a vector in standard form with the terminal point xy has component form v equals x comma y. The scalars x and y are called the components of the vector. We will now express the vector with initial point negative 3, 4 and terminal point 1, 2 in component form, and then we'll determine its magnitude. So let's go ahead and draw our coordinate system again. So I'll draw 5 ticks on the x in either direction. And I'll do the same for the y. So our vector v had the initial point of negative 3, 4. There's negative 3. There's 4, so there's the initial point. It had terminal point 1, 2. So there's our original vector v. Now we want to place the vector to have initial point of the origin 0, 0. Well, now we have to determine what the terminal point is. Well, how did we do it? Well, to move the initial point to 0, 0, we went down 1, 2, 3, 4 units. So the terminal point will have a y-coordinate of negative 4. We moved the initial point to the right 3 units. So our terminal point will have an x-coordinate of 3. Right? So we went down 4 units. We went to the right 3 units. So there's our terminal point. So there is our vector whose initial point is at the origin. Well, now what I'm going to do is let's now form a triangle. So here's our right angle. Now the height of this triangle is 4. The width I'm sorry, I messed this up. So let's start over. So we wanted the initial point at the origin. Where do we put the terminal point now? This is where I screwed up. The initial point moved down by 4, so our terminal point has to move down by 4. So 1, 2, 3, 4. The initial point moved to the right 3, so the terminal point has to move to the right 3. 1, 2, 3. So that's where our new terminal point is. Now while I'm at it, I might as well find component form. So the component form of V, remember, is just the terminal point. So where did our terminal point end up? Well, it has an x-coordinate of 4 and has a y-coordinate of -2. So the vector V in component form is 4, -2. Now let's go ahead and draw that right triangle again. All right, so it has a height now of 2, has a length of 4. So the magnitude, the length of the vector V is the hypotenuse. So hypotenuse squared is equal to 2 squared plus 4 squared, which means that the magnitude of V is equal to the square root of 4 plus 16. So the magnitude of V is the square root of 20, or 2 square root of 5. Now notice, if we look at the component form 4, -2, well, 4, isn't that 1 minus -3? And -2, isn't that 2 minus 4? So from this, we can now make a couple observations. The first one being, if v is a vector with initial point x0, y0 and terminal point x1, y1, then we can express v in component form as x1 minus x0, comma y1 minus y0. That is, the x-coordinate is the terminal coordinate the terminal x-coordinate minus the initial x-coordinate. The y-coordinate will be the terminal y-coordinate minus the initial y-coordinate. Now if we go back and relook, right? Well, looky here. Negative 2 squared is 4. 4 squared is 16. So if v is x comma y in component form, then the magnitude of v is simply the square root of x squared plus y squared. So it's the square root of the sum of the squares of the coordinates, or of the components. Now that we know component form, we can define the vector operations algebraically. So v is the vector v1, v2, w is the vector w1, w2. We're going to let k be a real number, so this just means k is a real number. Well, then k times v is kv1, kv2. And v plus w is v1 plus w1, comma v2 plus w2. Right, so in words, to do the scalar multiple of a vector, just multiply each component of the vector by k. To find the sum of two vectors, we just add the corresponding components. Let's now look at some properties of vector operations. So we're going to have u, v, and w be vectors in the plane, and we'll let t and s be scalars. First, the commutative property for vector addition says that u plus v is equal to v plus u. In other words, the order in which you add vectors does not matter. Associative property, the quantity u plus v plus w is equal to u plus the quantity of v plus w. So how you group vector addition does not matter. The additive identity, u plus the zero vector is u. So adding the zero vector to any vector doesn't change anything. The additive inverse, u plus negative u is equal to the zero vector. Let's now look at associativity of scalar multiplication. R times the quantity of SU is equal to the quantity of RS times U. So in other words, you can just multiply the scalars first and then take the scalar multiplication. Distributive property, R plus S times U is the same as RU plus SU. So scalar multiplication distributes across normal addition of real numbers. It so happens to distribute across vector addition. So R times the quantity u plus v is RU plus SU. That's not right. Sorry. Let's fix that. This should be plus R times v. The identity property for scalar multiplication, 1 times u is equal to u. So multiplying u by the scalar 1 doesn't change anything. And finally, the zero property. 0 times u is equal to the 0 vector, and so is r times the 0 vector. So if you multiply any vector, scalar 0, you get the 0 vector. And if you multiply the 0 vector by any scalar number, you also get the 0 vector. So we're going to look at the proof of property 1. So let u be u1, u2, let v be v1, v2. And then u plus v. Well, you get u1 plus u2. I'm sorry, u1 comma u2 plus v1 comma v2. And this is equal to u1 plus v1 comma u2 plus v2 by definition of vector addition. But this u1 and v1, they're just real numbers. So is this u2 and v2. And we know that the addition of real numbers is commutative. So the order in which I add u1 and v1 doesn't matter. And same thing for the order of u2 and v2. So I can write this as v1 plus u1, comma v2 plus u2. Well, now by definition of vector addition, this is just v1 comma v2 plus u1 comma u2, which is simply v plus u, which is what we desired. And so the proof is complete. The proofs of the remaining properties are done in a very similar manner, and so these are left to the viewer. Now let's expand upon component form a little bit. If we now consider this right triangle, so it has sides of x, y, magnitude of v, and an angle theta. Well, cosine of theta would be x over the norm of v. And sine of theta would be y over norm of v, right? Remember, cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. So if we're given the magnitude of a vector v, with the angle that it makes with the positive x-axis, then we can write v as the norm of v times cosine of theta, comma, the norm of v times sine of theta. In other words, the x component is norm of v cosine of theta, the y component is norm of v times sine of theta. So let's find the component form of a vector with magnitude 4 that forms an angle of negative 45 degrees with the positive x-axis. So v would be the magnitude times the cosine of the angle, so negative 45 degrees, magnitude times the sine of the angle. So cosine of negative 45 degrees is negative square root 2 over 2. And it happens to be the same for the sine of negative 45 degrees. And so our component form of v is negative 2 root 2, negative 2 root 2. So sometimes we're more interested in the direction of a vector. So we define the unit vector as a vector that has a magnitude of 1. Given any non-zero vector v, if we wish to find a unit vector in the same direction of v, which is denoted e sub v, the most logical thing to do would be to multiply v by 1 over its magnitude. Let's check this. Now notice that the magnitude of v is always going to be greater than 0 because v itself is a non-zero vector. It is left to the viewer to show that the only vector with magnitude 0 is the 0 vector. So we would have that 1 over the magnitude of v is greater than 0. So the direction is unaffected. So by multiplying the vector by 1 over its norm, its magnitude, we don't change the direction. Now if we take the magnitude of this, so take the magnitude of 1 over the magnitude of v times v. Well, 1 over the magnitude of v is a scalar, so this is scalar multiplication. So this will have magnitude of the absolute value of 1 over magnitude of v times the magnitude of v. But since 1 over the magnitude of v is positive, we don't need the absolute values. So we're left with the magnitude of v over magnitude of v, which is 1. And so this is indeed a unit vector. So the process of finding this EV is called normalizing the vector v. So let v be a non-zero vector in the plane, then the vector EV equals 1 over magnitude of v times v is a unit vector in the direction of v. So we have a vector 1, 2. We want to normalize it. Then we also wish to find a vector w with the same direction as v with magnitude 7. Right, so let's first work on normalizing it. So the first thing we need is to find its norm. So this is just simply the square root of 1 squared plus 2 squared. So we get root 5. So the unit vector in the direction of v is 1 over the square root of 5 times the vector 1, 2. So we get 1 over root 5, comma 2 over root 5. So to find a vector of magnitude 7 in the same direction as v, well, we already have a unit vector in the direction of v. We just found it. So why don't we just multiply this by 7? And that should give us w. Right, so this EV behaves as just the direction of v. So now w, 7 times 1 over the square root of 5, comma 2 over the square root of 5. And so a vector of magnitude 7 in the direction of v would be the vector 7 over the square root of 5, comma 14 over the square root of 5. There is a third way of representing vectors, as a sum of the horizontal and vertical vectors. So to do this, we need the standard unit vectors in the plane. There are two of them. Anyone who has studied physics would recognize these. You have I, which is 1, 0, so this is the x direction. And then you have j, 0, this is the y direction. So given a vector v equals xy, we can write v equals xy as x0 plus 0y. So this is the horizontal component plus the vertical component. Well, factor on x, you can have x times 1, 0. Do the same for y, plus y times 0, 1. Well, this is simply I. This is j, so we have xi plus yj. And this is typically the representation that is used in physics. Now, when writing ij by hand, again, it's difficult to write bold, so we'll typically use a hat. So we'll write I as I hat and j as j hat. Right, so read as I hat, j hat. You could also put an arrow over them, and that's also acceptable. Let's conclude with an application. So J.R. is stuck in the mud. Lisa and Jed come along in a truck to help pull her out. They attach one end of a tow strap to the front of the car and the other end of the truck's trailer hitch. And the truck starts to pull. Meanwhile, Jane and Jed get behind the car and push. Now the truck generates a horizontal force of 300 pounds on the car. Jane and Jed are pushing at a 15-degree upward angle and generate a force of 150 pounds on the car. We wish to find the resultant force. Give its magnitude to the nearest tenth of a pound, its direction angle from the positive x-axis. In other words, we wish to determine the total force on which this car is being pulled. Well, in physics, typically the first thing you want to do is you want to create a force diagram. So we can treat a car as a point mass. So let's say there's our car. Now the truck is pulling horizontally with a force of 300 pounds. They are pushing from behind with an angle of 15 degrees, an upward angle of 15 degrees. So it kind of looks like this. They're behind, they're doing something like this, and it's 150 pounds. Well, remember, we can place the vector however we want. So let's just draw up here. And then this angle is 15 degrees. So we no longer need this. So here's our force diagram. So let's call force 1 300 I. Force 2. Well, force 2 has a magnitude of 150 pounds with a 15-degree angle to the positive x-axis. So it'd be 150 cosine of 15 degrees I plus 150 sine of 15 degrees J. The total force is the sum of forces. That is, it's F1 plus F2. So we have 300I plus 150 cosine of 15 degrees I plus 150 sine of 15 degrees J. That is, it's 300 plus 150 cosine of 15 degrees I goes on the outside, then plus 150 sine of 15 degrees J. So the horizontal component of this force is 300 plus 150 cosine of 15 degrees. The vertical component is 150 sine of 15 degrees J. Or not J, just 150 sine of 15 degrees. We were asked to find the magnitude. So we want norm of F. Well, this is the square root of 300 plus 150 cosine 15 degrees all squared plus 150 sine of 15 degrees squared. Plug this into a calculator to the nearest tenth, you should get 446.6 pounds. Now notice that I waited until the very end of the problem to round my answer. This is good strategy. This is convention. The more rounding you do throughout a problem, the more error you will accumulate. So in general, you should always wait to the very end to round. So there's our magnitude. We now need to find the angle that it makes with the horizontal axis. So I'm going to keep everything except this magnitude. So to find the angle, we make use of the relation tangent of theta is equal to y over x. Right, again, to see this, here's our right triangle, x, y, theta. Tangent of theta is opposite over hypotenuse. So tangent of theta is the y component divided by the x component. Or it's the vertical component divided by the horizontal component. Now, since both the vertical component and the horizontal component are positive, we can go ahead and take the inverse tangent of both sides. So theta is the arctan of 150 sine 15 degrees over 300 plus 150 cosine of 15 degrees. If you plug this into a calculator, you should get approximately 5 degrees. So remember, the magnitude was 446.6 pounds with a direction of 5 degrees above the horizontal. So that concludes vectors in the plane.